So, hello Arvind. Hello Arun. Please introduce yourself.
Good evening, sir. My name is Arun Singh, and I completed my graduation in 2022 from Punjab Jain College, Chandigarh, in mechanical branch.
Okay.
And during my graduation, I was the part of BAHA SAE, where I was the head of the sub-team manufacturing and transmission. Also, I was responsible for the efficiency during the manufacturing. That's it.
So, what are your favorite subjects?
Sir, my favorite subjects are fluid dynamics and heat transfer and strength of material.
Dynamics, heat transfer, strength of materials. Okay.
So can I on the fan for a second? It's so hot.
Yeah, fine.
हेलो, am I audible?
हाँ सुबोध.
अभी audible हूँ?
Yeah, you are audible.
That's good.
Yeah, so Subodh, would you like to start with questions or?
Yeah, you please go ahead and then I'll join.
Okay. ये क्या हो रहा है?
Okay, let's go.
Okay, let's start. So, Arun, you said you like fluid mechanics, fluid dynamics, right?
Yes, sir. Yes, sir.
So, can you tell me the difference between a laminar flow and turbulent flow?
Okay, like in laminar flow, the fluid particle they follow their streamline. They do not change the path. Like they do not. The flow is so smooth. The fluid doesn't have a eddy velocity. Like the fluid doesn't travel from their part to the another fluid particles. In turbulent flow, the fluid flow from here to there during their flow.
There are some characteristics of a turbulent flow, like we can say properties of turbulent flow. Can you name any? You are right. Your definition
In
of
turbulent flow,
there are some well-known characteristics or properties.
Sorry, sir, I'm not getting it.
So there are some properties of turbulent flow, like it is we can say based on see, there is no one fixed definition of turbulent flow, but we have come up with some, let's say 5-6 characteristics. One of them is it is being unpredictable, it is been transient in nature, and something like that. So that's what I wanted to come up with.
Property.
Okay, it's all right.
Sorry, sir, I'm not getting right. I'm not getting the point in what way you are trying to ask.
Okay, so it's actually a little bit theoretical part. So what I will do is once the session is over, I'll get back to you and then we'll let you know. Okay. Yeah.
Okay. So, fine. Next question that I would like to have on fluid mechanics is, can you draw a velocity profile for a fluid that's flowing over a plate or a channel that has pressure gradient applied over the two ends?
Pressure gradient over a flow over a flat plate.
I have a plate, or you can say a channel, rectangular channel, through which fluid is flowing. There is a pressure difference between the 2 points, or you can take it as a cylindrical pipe. Basically, what I was hinting towards is flow in between a slit. Okay, but we can take it to a pipe.
Yeah, I got it. Like that we call a Cauty flow, right? Cauty flow.
Yeah.
That's So it will somewhat like parabolic.
Sorry.
Like something like parabolic shape, velocity profile.
Okay, it should play the parabolic shape. And can you just draw and show like where will be the velocity maximum, where will be the velocity minimum?
If you have marker or sketch pen, please use that, because like pens are little bit hard for us to see.
I mean, just draw and show.
Yeah.
Can you hold it little down, little down. Okay. So what will be that minima? Will it be 0 or?
Sir, it will be 0. It's if it is a channel.
Okay. Now I just have two immiscible fluids flowing through the same channel. Okay.
Okay.
So how will be the velocity profile? Consider mu1 greater than mu2. There are two perfectly immiscible fluids that are flowing. So they will make two layers.
Okay, I got you. Sir, mu1 is upside now.
You can consider it on the top. Mu1 to be greater than mu2.
Mu1 is wait a second, I need to think.
Instead of directly jumping
I'm
to
taking the equal thickness.
You can take equal thickness.
I will mention the
Okay.
Can you say?
Yeah.
Like mu1 is greater, so there will be the greater influence of viscosity. Like it will influence more layer with the velocity which is 0 from the surface, no? So there will be more influence to that.
Okay. So hence you are saying that it will have a my question is
सर मेरे को like intuition से मतलब मुझे अभी तक इतना yeah.
So my only question to you is where will be the
intuition से actually ऐसा लगा जैसे maximum can be like at the interface.
Maximum can be at the interface. Okay.
Yes. Like
So
पहले वाले fluid का viscosity ज़्यादा है ना?
What is the condition at the interface? So you will need some boundary conditions, right? So what are the boundary conditions at the interface?
Yes. The slope will be same, like du by dy.
No. Velocity will be same. No slip condition.
Sorry, velocity will be.
So, and can you think of one more boundary condition? Can you think of one more boundary condition? You are right. Velocity will be same. So, is there any like more boundary condition you can think of at the interface?
At the interface, the shear force.
Yeah. So, can you formulate it? What will be the expression?
Do I need to equate the shear force?
Like, what do you think?
So I think the shear force will also be same.
Why?
To balance the force, like from both the side, both fluids should uh, apply the same force on each other.
Correct, correct. So, what's the expression?
Mu to del u by del y.
So that's not an
Wait, I will
expression.
write
That's
it.
a, like a term.
The expression, I'm not
Yes.
getting it.
So, for example, you just said that velocity will be equal at the interface, right? So, how can you write it down? You can
Yes, sir.
write it down, yeah, u1 equal to u2, right?
Hmm.
So, what can you
Yes, sir.
say something like this about the shear force?
Sorry, sir, I'm not getting.
Okay. So, what will be the shear force in fluid one? What will be the shear force at the interface?
At the interference,
Yes.
it will be u1 into du by dy. Mu1 into du by dy
Correct. And this is for fluid one. Now, what will be for fluid two?
with the Newton's law. Yeah, that will be mu2 into du by 2 by dy.
Correct. Now, you said that both of them will be same, right?
Yes, sir.
Yeah. So, can you write it down?
So do you want me to write this?
Yeah, yeah.
Is it
Yes.
visible?
So, correct, correct. So, this is what we actually expected.
Now, if you just
Okay.
think on these two boundary conditions, okay, do you think that the maxima should occur at the interface?
Maximum velocity.
Yeah, the maximum of the velocity. Or what is the condition?
Maximum can occur, but it's not necessary that maximum will occur at the center.
No, maxima will never occur at the interface if viscosities are different. What is the condition to get pen paper?
But your voice is stuck.
What is the
Your
condition?
voice was stuck.
What is the condition to get the maximum velocity? At which plane will
du
we
by
get?
dy must be 0.
Correct. So will it be 0 at the interface?
No, like shear force is existing.
So now where do you think will be the shear zero plane? Will it be in the lesser viscous fluid or the higher viscous fluid?
Zero shear plane.
We can say plane of the zero
Yeah,
shear stress.
I got your point. I got your point. You mean that where will be the maxima in the first one or the second? Sir, I think in the second one, which have the lower viscosity.
Exactly. So there we'll have the maximum velocity. Okay.
Yes, sir.
Correct. Now, go back to your diagram once. Now, can you draw a new diagram, because that's not a very correct one. So, can you update it? And please keep mu1
Yeah.
greater than mu2.
Okay, sir. Is it something like this?
Right.
Right.
And there will be some sort of distortion at the interface. It will not be a smooth value, but there will be a slight distortion because the velocities have to be equal and shear rates have to be equal. So that will be covered.
Okay, sir.
So your first favorite subject was fluid dynamics.
Yes, sir.
One last question on fluid and then we go to heat. So can you define friction factor in a turbulent flow? How do we define friction factor?
Friction factor in turbulent flow.
Or let me simplify the question. I have a system of pipes through which fluid is flowing and I need to calculate the losses. So how will I accommodate the loss due to friction?
So I think there was many method that was proposed for the turbulent flow to calculate the friction factor. Actually, I can't recall that area right now.
Mostly use charts, Moody's chart.
Yeah, Moody's chart.
Okay. And then we incorporate the term like 4F L by D V square by 2G in the delta P term. So we incorporate every loss as a head loss. 4F L by D V square over 2G.
Yeah, it is the same Darcy-Weisbach equation, but we have a modified friction factor here, which we obtained
So
from the Moody's
can we
chart.
use this for turbulent too?
Yeah.
Yes.
Okay.
So based on that, because you asked this, what is the F here in case we are in a laminar flow?
It is 64 by Reynolds number.
Correct. So
for the flow through the pipe.
Correct. Now, in case it's a turbulent flow, then we cannot equate the F with 64 by Reynolds number. In that
Yes, sir,
case,
yes,
we have some another F which have been usually experimentally derived, and we get it from the Moody's
yes,
chart.
sir.
Okay, so a Moody's chart has, let's say, L by D ratios given. Based on that, we come up with the F for a given Reynolds number.
For the different Reynolds number, we calculate the F from the Moody's chart.
Correct. I won't say we calculate, we observe, like what's the value given.
Like we observed.
Correct.
Sorry.
Okay, so now let's move to heat transfer. So, Arun, what are the different modes of heat transfer?
Commonly, there are three modes of heat transfer. Number one is conduction, number two is convection, and number three is radiation. But nowadays, people say four mode of heat transfer, which we call as evaporation. Like basically, that's a process for the cooling. Evaporation, fourth mode of.
That's new for me as well. I worked in condensation, but okay, fine. It's actually a combination of conduction and convection, mostly convection.
Yeah.
So please don't say it's
And
a
that's
fourth.
why I say people nowadays say like.
That's okay, but please don't call that as a fourth mode of heat transfer. There are only three. Okay. I highly doubt it's something like that exists. Okay. So, so can you please give me what are the ways through which these three modes works? I mean, what are the principles behind it? How do they exactly work?
So, sorry, sir, your voice.
Okay, so my question is, what are the ways through which these three modes work? What is the basis of conduction? What is the basis of convection? And what is the basis?
Okay. The conduction. The reason behind the conduction is in the metals. The main reason is the free electron and the lattice vibration.
Mm-hmm.
And in the like for the solids, and mainly for the metals, it is free electrons, and for the non-metals, it is lattice vibration. And for the gases and the vapor, it is the momentum diffusion.
Correct.
And the convection, the convection. In convection, we have the two types of convection. One is forced convection, and the second one is the free convection. In the forced convection, let's suppose there is a hot plate. We force the air to flow over the hot plate. In convection, first of all, when the forced air uh, when the forced air get in touch with the hot plate, the nearest layer gets stuck to the hot plate. It will be stationary, and that the first layer, the first of all, conduction happen, and through that first layer, the another layer get hot, and so on, the heat transfer to the next layer, and the air is forced, and the hot air move away, and again the cool air comes in the way, and in this way the forced convection happen.
Correct. And in
Did you get my
radiation,
point?
yes, we did. Although what you said was the types of convection, but but you were right. And how does the exactly radiation works?
Sorry, I missed the point. It is due to the bulk motion of the particles in convection.
Correct. And what about radiation?
In radiation is the electromagnetic waves which transfer the heat from the one body to another body.
Right. Now let's say I want to design a thermos flask. Okay. So
Yes.
how one can approach this problem? Now, what is thermos? We want to store our
Yes,
hot fluid or cold fluid, so that there should be less to no heat transfer from the surrounding. What are the ways through which you can design a good thermos? We can say it is a container. It has some
okay.
walls. So, if you are given some freedom to design a thermos, how would you approach the problem?
So, like I will take the three layer in the thermal flux. The inner
Mhm.
one will be the uh, material suitable for the containing our liquid, whichever the
Correct.
food or the liquid we want to store. The second one, I will keep the insulator, the highest with the lowest thermal conductivity.
Okay.
And the last one will be the for the protection of our thermal flux, the strong material.
Yeah, that's a really good answer. Now, can you think something better for as an insulator? Can you think something which is even better than an insulator? You're right.
A foam type material.
Correct. But can you
Like
still do even
I
better?
didn't getting the that was inward. Me, I'm not getting the name of that material right
Refractories are called. Those are kind of refractories, but okay.
now.
But
Those are the refractory material.
correct. But those
But
are
I
very
think we
heavy and
can't
all.
use that.
Correct.
Yeah,
Those are very heavy and
we
could be
can't use
little
them in a
costly.
thermoflask. There is some foam like material. I'm not getting the name right now.
That's actually it's very well known what one should optimally use. So what if we put in air there?
Air can also be a good insulator. Like it has a very low thermal conductivity.
Correct. Now what if there is a vacuum?
That will be the perfect thermal flux.
Exactly. So
If we will be able to put the vacuum under.
correct. So there will be less to no convection, less to no conduction. There will be only maybe
Yes, sir.
whatever it is
Only
radiation.
radiation.
Correct.
Yes.
Now there could have some other design challenges, but the point being, it will be a good thermos, right? Yeah.
Yes, sir.
So I would say let's end it for you as of now. Uh, okay,
Okay, sir.
Nachiket, anything?
Sir, I have a question.
Mm-hmm.
Like these interview happens on every weekend for both days, Saturday and Sunday, right?
Yeah, we try to do as much as we can. But yes, yesterday there was some issue, So we are conducting it today.
Okay. Okay, sir.
Good.
So when
So,
will I get the report on my this interview?
hmm?
When will I get the report on this interview?
Yeah, we'll let you know actually. So because
Like,
let us first complete the interviews, then we'll get back to you.
okay, sir.
You are
Should I-
mute, Nachiketa. You are mute.
You can just stay back in the call and look for others interview as well, and towards the end we'll discuss one-to-one comments, right?
Okay, sir.